Hi folks, in this video we review our new logical system prop. What we're going to do is some practice translations as well as assess some arguments. So here's your first task. Pause your videos now and see which from this big list should be correctly translated as H arrow M. So pause your videos and see if you can figure this out. Okay, let's talk about the answers. The easiest ones for me to latch onto are the if-then claims, and there's a couple of them here. So when you see the word if alone, that's just a standard if-then claim, and if always signals the antecedent. So M if H is the same thing as saying if H then M, and that's why this red one is the correct translation. Only if is slightly different. So only if actually does read left to right. The antecedent is the furthest thing over here to the left. H, because something is a horse only if it's also a mammal. All horses are mammals. The same thing is put with sufficiency. So only if and sufficient are actually synonyms. Saying H is sufficient for M means satisfying this thing, being a horse, guarantees you it's sufficient to make sure you're also a mammal. The concept of a necessary condition is different. So necessary and sufficient are not synonyms. They're related, but they are actually inversely related. So if H is sufficient for M, that means M is necessary for H. So we cannot put this one. It's not true that H is necessary for M. That's the wrong direction. Similarly, notice the if here alone, this is the wrong direction because this would have M in the antecedent. But notice over here, the thing we're translating has H in the antecedent. Now, what about IFF, if and only if? This is not correct because this arrow goes in both directions. We need a biconditional. Just in case is also the same as the biconditional, so that's not correct. Whenever, this is actually the same as if. So if I say like, whenever M is true, then H is true. That's just like saying if M is true, then H is true. So this is the wrong direction. This is going in the wrong way. So there's only 3 correct translations. What we're doing here, we're reviewing the logical system prop. And prop is just like bool, only more. It's got more stuff to it. What we've done is we've just added 2 new truth functional connectives, the conditional and the biconditional. We're giving them truth functions, and then we're also going to learn how to do some formal proofs with them. In order to do the formal proofs and learn how to actually argue with these things, we need to start assessing how they figure in arguments. So let's do some practice here. Here's 4 sample arguments. What I want you to do is tell me which of these is valid. So pause your videos now and see which are valid and which are invalid. Okay, that was your chance to pause your videos. The first one, let's take A. This one is clearly valid. This is just our inference modus ponens. This says if P then Q and P, so of course Q has to follow. That's just what the arrow means. So this is like the canonical form of reasoning from conditionals, and it should be quite obvious why this is valid. B is a little less intuitive, but B is also valid. Here's one way to try to make sense of it for yourself. B, the contrapositive of my premise, P arrow Q, is not Q arrow P. And now it makes sense why if I give you not Q as another premise, we can also figure out that not P has to follow. So this one is like doing modus ponens on the contrapositive, basically, is one way you could think about it. Now, you know, logicians have loved this inference for so long, they give it a name too, modus tollens. You do not have to remember this name, but I do want you to remember MP, or modus ponens. All right, how about C and D? Which of these is valid? Well, hopefully you could assess that C is not valid. How could you prove it? What you should do is use the truth table method. So let's do a joint truth table. My 2 premises here, and then this little line, remember, signals the thing after it as the conclusion, and then P is my conclusion. I just have to look for the counterexample and look at row 3. On row 3, the premises are both true and the conclusion false. This is actually a famous fallacy called affirming the consequent. In a sense, no, remember, the arrow does not go in both directions. Only the biconditional goes in both directions. So P arrow Q does not mean Q arrow P. And so it's incorrect to assume if you get Q, you can infer P. That's like trying to go in the opposite direction, but that does not work. So that's invalid. How about D? Did you figure this one out? This is invalid for the exact same reason. This is sort of like affirming the consequent on the contrapositive, or people also call it denying the antecedent. It's just another name for the exact same concept. The same counterexample, row 3 is still the problem. So this is also invalid. Just because, you know, P guarantees Q and not P is true, that doesn't guarantee not Q is true. Maybe several things guarantee Q. You know, if P then Q and if R then Q. And even if I don't have P, maybe I've got R. So you can see why this is not a valid form of reasoning, or that that truth table demonstrates it conclusively. Okay, so that was our review of our new logical system prop. What we're going to start doing now is some formal proofs with them. Thanks.